Section 1.7, the components of a vector. So if we think back to the example we saw of the car that we said went 2 miles, but we didn't know the direction until the direction was specified, right? That, okay, it went 2 miles in this particular direction. And then we had the path of the car that's this R vector from start to finish. Well, we can break down this R vector into what's known as X and Y components of the R vector. And you can look at it, and the X one is purely in the horizontal or X direction. The Y component is purely in the vertical direction or the Y direction. And if we add these together, we'd have vector X is pointing to vector Y that are lined up that they can do vector addition. So X plus Y is equal to R. So you can use these two vector components as opposed to the resultant vector. And it's often much easier to work with vectors that are perpendicular, that are purely horizontal or vertical, as opposed to ones that are at some odd angle in between. So this is working in terms of the car example, but we could instead call it vector A as opposed to vector R. And then we could break vector A into an X component and a Y component. So this is just like on the similar slide, right, where the X component is purely in the X direction, the Y component is purely in the Y direction. And these two vectors are always perpendicular to each other. We can see that right angle there. So the X one is parallel to the X axis, Y is parallel to the Y axis. And this is the way that they're drawn for a proper vector addition, right, where the tip of the X component of A points to the tail of the Y component of vector A. But it's just as accurate to draw it with both of them on the axes, because we can shift these freely. That doesn't actually change the vector as long as the orientation stays the same. So as long as we aren't changing the orientation of being up or down or changing the length, then we're free to shift them like so. And added vectorially, the overall vector A is equal to A sub X plus A sub Y. The other way to think of this is these components are sort of like a shadow, right? You could imagine perhaps looking from the right side over here at this, if this is an eye, right? And as you're looking at vector A, you could see how much of it is pointing in the vertical direction. So the shadow of vector A would give you this A sub Y component. Similarly, the shadow onto the other axis, if you're now looking from above, then vector A, you would just see this X component, A sub X, because that's the shadow of the total vector. So the components can give you more information in that regard. Right, now the vector components are a little hard to work with because they're still vectors, but we can get around that if we instead work with the scalar components. So instead of being A sub X vector or A sub Y vector, we can work in terms of AX without the arrow on top. Right, so the vector component has this arrow up on top, and that's what makes it a vector component. As opposed to the scalar ones have no arrow. And the way that we can write this vector component in terms of the scalar component is by using unit vectors. So unit vectors, I like to think of these as pure direction. They don't add any length because their length is just 1. So they aren't able to change the length. They just specify the direction. So the X hat is what's called that little symbol above. The X hat is purely in the X direction, and the Y hat is purely in the Y direction. So we can instead write vector A as equal to scalar component AX times X hat unit vector plus scalar component A sub Y times Y hat unit vector, right? Where what we've done here is we've filled in, instead of AX vector, we've filled in the scalar component times this unit vector. And the scalar component we'll see is so much easier to work with. So we really like to work in terms of the scalar component of the overall vector. And here it shows the X hat vector. It's just a length of 1, but it's purely in the X direction. Y is purely in the y direction. Alrighty. So let's try an example of this. A displacement vector has a magnitude of 175 meters and points at an angle of 50 degrees relative to the x-axis. Find the x and y components of this vector. So to start out, we want to try and draw this. It says the vector has a magnitude of 175 meters. That tells us how long the arrow should be. And it points at an angle of 50 degrees relative to the x-axis. So if we picture having our axes on there, right, that y is purely up and x is traditionally to the right, then this displacement vector has to be 50 degrees above the x-axis. So something like that. And so that angle would then be 50 degrees. And the length of this is the 175 meters. Cool. Now we want to find the x and y components of this vector. In other words, we want to know how much of the 175 meters is pointing purely in the x direction and how much of it is pointing purely in the y direction. So to draw this in, we could draw it any number of ways. But one is we could draw our x down below because we've been using that a bunch. And so this would be my x component. And then let's get a different color for the y. So the y component would be the shadow in the vertical direction, y. And then we want to try and solve for x and y based upon the angle and the length of this resultant. And the way that we can do that is by going back to our trigonometry. This is where it's all going to start coming together. The way I've drawn this, it doesn't look much like a triangle, but we can shift one of the vectors to make it more of a triangle. Since we already have this 50 degrees angle labeled, I'm going to move the y vector so that it's part of the triangle with this 50 degrees. So I'll draw my y over here instead. It's still the same, I haven't actually changed anything. And we notice that we have this right angle between the x and the y that will always be there. So we now have a right triangle. That means we can solve this. Totally, absolutely, which is great. So let's start with the y because why not? So with the y, we want to think of a trig function that will allow us to relate the angle, this y component, and the long piece, the 175, which notice this is our hypotenuse. And the y is our opposite side. So what trig function has the opposite in the hypotenuse? That's our sine. Right, so I'll just write this up here. Sine of theta is equal to y all over the hypotenuse. I'm going to write it as h for now. All right, now let's do the same thing for the x component. For the x piece, we notice it's the side that is right next to the angle or adjacent to it along with the hypotenuse. So if this is our hypotenuse, then the adjacent and the hypotenuse is going to be our cosine. Right, so cosine of that angle, which is 50 degrees, is going to be equal to the adjacent side x divided by the hypotenuse. Now the reason I left it in terms of the angle theta and the hypotenuse is this now gives you actually general equations that will work for your x and y components. As long as your angle is defined relative to the horizontal, to the x-axis, then you can solve for x by multiplying that hypotenuse by both sides. So x is equal to h times cosine of theta. And you can find y in the same way by multiplying the h across. I'm just flipping the order here. So y is equal to h times sine of theta. So these are two great equations to keep in mind. If you prefer really strongly to work with numbers, then you can also do that. But I encourage you to try to think in terms of symbols. I know it feels really foreign and strange and scary, but it will help you out this semester in physics if you can embrace the more abstract notation. All right, so this is the basic process. that we can then take over here. I'm going to clear my drawings to make it cleaner, but we see that we can get the y with the r, they used r instead of h, times sine of theta, and the x with the r times cosine of theta. And there they plug in the numbers that the total length is 175 meters, and then the angle is 50 degrees. So that gives us for y, that's 134 meters, where the units still matter, and for the x, that's 112 meters, right, where the units matter. So those are the two components, but we could also write the overall r vector is to have the true components and not just the scalar components, that r is equal to 112 meters x hat plus the scalar y component, 134 meters times y hat. So this would be the most complete way to write your final answer. One other note here, we could have solved this with the other angle alpha. This angle is defined relative to the y-axis or the vertical, so we'd have to switch our sine and cosine around. So that's why we often won't use that angle. We'll often try to use the one that is defined relative to the horizontal or to the x-axis. And that often works much better for us. So we'll wrap it up there, but we'll be able to use these components in the next section in order to have an easier method of adding our vectors. So stay tuned.